I'm Jihee Park, and today I'll present our work on bridging the gap between real-world and formal binary lifting through filter simulation. This is joint work with Insu and Sukyoung. Binary lifting translates low-level machine code into a higher-level intermediate representation, enabling binary analysis at a higher level of abstraction. To ensure that the IR represents the machine code correctly, we need to formally define the semantics of IR and prove the correctness of binary lifting. Consider this simple C function, which allocates an array of size 2, assigns 1 to its first element, and returns that element. The compiled machine code for this function also will always returns 1, so the lifted program also should returns 1. In this simple case, it is straightforward to represent the behavior of machine code into IR. However, the problem arises when the machine code have more behaviors than the source code allows. Consider this modified function, which writes to the array at index I. If I is out of bounds, such as 2, then the compiled machine code will still perform some operation. For example, it will corrupting the stack frame or writing to arbitrary memory address. Because of these exotic extra machine code behaviors, it becomes challenging to precisely capture the semantics of the machine code into IR. We observed that real-world binary lifters do not represent all behaviors of machine code. Instead, it considers only execution that satisfies implicit assumptions when it analyzes and optimizes the machine code. The assumptions in lifters are inferred from machine code by combining static analysis and compiler-specific heuristics. For example, if the lifter assumes the valid stack range of the function as -16 to 0, any memory access outside this range is considered as an assumption violation and excluded from the analysis and optimization of this IR. This observation plays a crucial role in defining the correctness of real-world binary lifting. Based on this idea, we formalize assumption-based binary lifting, which is behavior of the real-world lifters. More specifically, we identify 3 key transformations of binary lifting which uses assumption. Next, we define correctness of binary lifting as a filter simulation, a variation of bisimulation that considers assumptions. Finally, we implement a prototype binary lifter and evaluate it on x86-64 Linux binaries. So, to begin, we manually analyze the real-world binary lifters and identify 3 kinds of transformations which use assumptions. First is control flow graph reconstruction, which analyzes the flow of execution between basic blocks and enforce bounded control flow within the function. Second is abstract stack reconstruction, which infers the structure of the stack and optimizes stack pointer-based memory accesses. The last is function input and output identification, which annotates function calls with their inputs and output registers, enabling further optimization through callee saved and caller saved register information. We formalize these transformations and show that they satisfy some property which we define the correctness of lifter. Now, I'll explain about the formalization of correctness for assumption-based binary lifting. The core concept of our formalization is a lifting relation that connects a trace of the low-level program with a trace of the high-level program, but it does not require extra high-level program. It consists of assumptions, low-level program, a low-level trace, and a high-level trace. We color the low-level components in pink and high-level components in blue. For the example program, when the assumption specifies the valid stack range as -16 to 0, and the low-level program which uses memory relative to the stack pointer, the low-level trace which uses concrete global address for stack addresses, it refines to a high-level trace which uses abstract functional local addresses. After we defining the filtering relation, which is a relation between two traces, then we define a relation between low-level and high-level programs called filter simulation as the proposed correctness for binary lifting. It consists of assumption, a low-level program, and a high-level program, and the equivalence relation between low-level and high-level trace. In this abstract stack reconstruction example, the equivalence is defined by exact equality of trace when substituting abstract pointers to concrete address given in the low-level trace. The formula below states the formal definition of filter simulation in paper, and I'll now explain this with this given example. Filter simulation consists of two parts of simulation, backward and forward. The backward case is just like a traditional definition of simulation. In example, consider two traces in correspondence. The low-level trace has a concrete stack pointer value, while the high-level trace has an abstract one. And suppose the high-level trace take another step, then the low-level program must follow the corresponding step, such as assigning X to corresponding concrete stack address. This is just a rephrase of traditional simulation in our formalization. But the fourth case is a bit different than traditional simulation. Like a previous case, we suppose the low-level program extends its trace, but then it additionally requires some high-level trace related by filtering relation to ensure that this low-level trace does not violate assumptions. If it has the filtering relation with some high-level trace, then it must follow corresponding step in the high-level program. So in this example, the low-level program accesses stack memory within the valid stack range. Therefore, it should exist a corresponding trace in the high-level program which accesses with abstract stack pointers. However, if the low-level program accesses memory outside the valid range, then there is no need to find the corresponding trace at a high-level program. This reflects the idea that not every trace from the low-level program needs to be matched with the trace from the high-level program. This is the core idea of filter simulation. With this formalization, we implement a prototype lifter using filter simulation named FIBLE using Ghidra binary analysis framework and OOPSLA'25. It applies the three transformations sequentially, producing 3 layers of IRs with interpreters for each IR. We also implement emulation of Linux system calls to support interpretation of ELF executable for evaluation. It also includes a validator that runs 3 IRs simultaneously to check whether the filter simulation holds during execution. We evaluate our lifter in terms of expressiveness, correctness, and performance. Expressiveness means that by running interpreter, we check whether our inferred assumptions actually hold for compiled machine programs. Correctness checks whether the lifted IRs satisfies filter elimination for all programs, and performance measures the time taken for lifting. For evaluation dataset, we use 2 kinds of well-defined compiled C programs. First is Coreutils, and second is CGC dataset. Coreutils consist of small utility programs that commonly used in Unix-like operating systems, while CGC contains various small programs for cybersecurity research, especially for binary analysis. All programs were compiled with GCC using O0 option. For expressiveness, we run the interpreter of the lifted IRs with the given test suite and checks for assumption violations during execution of these tests. In result, it correctly inferred assumptions for over 70% of programs. Assumption violating cases involve uninitialized stack memory, some implementation specific behaviors like comparing local pointers with global pointers, and imprecise static analysis of our implementation. For correctness, all programs pass the validator, even if the execution was stopped due to assumption violations. For performance, we measure the time taken for lifting machine code. In result, most CGC programs complete lifting under 10 seconds, and most Coreutils programs takes about 1 or 2 minutes. It shows that our approach is efficient enough for practical binary lifting. There are additional details in the paper, including formal syntax and semantics of our layers of IR, and design of sound analysis with assumptions, for example, how to do control flow analysis for CFG reconstruction, and more extensive evaluation result, like comparing our lifters with practical lifters, and also for formal binary liftings. To conclude, we propose a new approach to formalize correctness for real-world binary lifting. We capture 3 essential analyses and transformations using assumptions, implement our approach for x86, 64 Linux, and successfully lifting Coreutils and CGC binaries with semantic guarantees. We believe this opens up promising directions for formal binary analysis. This is end of my presentation, and thank you for listening.
Any questions from the audience? If you have, then please come up to the microphone.
Thanks for the great talk.
Yes.
I was just wondering, is there anything specific about the free analysis, or could you in principle use the same technique for other kinds of transformations?
Thank you for a great question. That is because the all transformation in binary lifter shares the same theme that that excludes some behaviors of the low-level program by some their generated assumptions. So while the domain of assumption is different by the transformation, there is a common property that they only preserves the lower level trace when the assumption satisfies.
Okay, this makes sense to me. I guess I was wondering, is that likely to also be common for other transformations or other analyses?
What means other for binary analysis?
I guess I'm wondering whether these applications of your technique are examples of a more general space of, maybe I'm misunderstanding, but I think I was wondering if you could next extend the technique to apply to other kinds of transformations that are performed.
I think that's a great idea, but currently I just focus on the binary lifting, so I just...
Okay, thank you.
One short question is still possible, but please, while... Yeah.
Yes, thanks for the talk. And can you provide any comments on adapting your method to other architectures, such as with different APIs than the x86?
Yeah, basically our concept and theory is independent to architecture, but in practice, the implementation is it requires more engineering effort for implementing various kinds of architectures.
Okay, thanks.
Thank you again.